Good evening, and welcome to our 6th Design Essentials class, our final Design Essentials class for this particular course. Lots of tears in the audience, that's okay. There'll be more learning to do at another time. This evening, we're going to be talking about miscellaneous topics. All the stuff that didn't really fit in anywhere else. Those things, in particular, we'll be looking a lot at 3D printing and slicers, as well as some design for manufacturing, or you'll see it abbreviated as DFM. You might hear that come up. And then some game strategy we'll touch on a little bit. When you design parts for 3D printing, there are some things you should do to make your prints stronger, better, all around, more efficient. What are some of those things? Supports could be useful.
Lack of supports.
Lack of supports is better. Why is lack of supports better?
It's less print time, and it usually means that the print is stronger. Sometimes.
Debatable on the strength.
The type of material you're using.
Yep, that is definitely something you should be considering when you are designing your part. So the couple that I listed out here are you should fillet all of your corners where you can, because otherwise you have what? We talked about it before. What is it called in engineering, though? Stress concentrations. That is correct. You have stress concentration where? In the corners. That's why you fillet the corners. That's okay. You get stress concentrations in your corners if you don't fillet your corners. So you want to try and fillet it everywhere that you can. You should consider your layer line orientation. So before we go any farther, is everyone in the room familiar with 3D printing? I'm getting lots of yeses and maybe some mess. So just for a brief overview, who wants to tell us what 3D printing is, particularly FDM? Into the mic. Fused deposition modeling. It's the type of 3D printing that you're familiar with. Most familiar with.
Very small, thin layers of plastic on top of each other in the shape of the part that you made.
That is correct. You put it into a slicer. A slicer then generates a path for your print head to follow, and your print head lays down a bead of continuous plastic. And it does one layer at a time, moves up a little bit, and then does the next layer, moves up a little bit, so on and so forth, until you get your full 3D model. That is called FDM, fused deposition, because you're depositing the material modeling, as opposed to resin printing, which might be an SLA, stereolithography, or you have SLS, which is selective laser sintering. You have a laser hardening plastic in a particular spot, so it makes a cake of powdered plastic, and you end up shaking it and pulling the part out at the end, and you reuse all that powdered plastic. So there's lots of different types of 3D printing. Yes, sir.
Isn't that last one with the powdered plastic also applicable to powdered metal?
Yes, that is exactly right. There is SLS for metal. You most commonly see it with titaniums and steels, but it is for a metal 3D printing in particular. It's not really used for large-scale manufacturing because it's expensive and slow, but it is sometimes used for prototyping when you need to have it made out of metal, and that is one of the types of metal 3D printing. So you are correct. There's other types of 3D printing, but those are the ones that are most commonly used. So when you hear resin printing, it's usually SLA. SLA is usually weaker. So then FDM comparatively, if you're using the same materials. It's not always the case, but in most cases, FDM is way more cost effective anyway. So when talking about layer lines, when you put it into your slicer, the orientation you print it in, it's going to have layers of material. And it is very easy for you to take the print and put a lot of force on it in the same parallel direction as the layer lines and shear it right across the layer lines. Whereas trying to go the other way, when it's a continuous piece of plastic, it is a lot harder to get it to break. So you should consider what direction your layer lines are facing when you are designing the part. Maybe you need to put some features in so you can print it in an orientation that has the layer lines perpendicular to where the forces are going to be. You should be considering where supports are required. Where do you need supports?
Anywhere that hangs over the part that's not supported by anything beneath it.
That is correct. Most slicers will tell you exactly where you need supports. The more supports you have, the more time it takes to print, the more material you use. It doesn't necessarily mean a weaker part. Sometimes it is a better orientation for the part to print it with supports, as opposed to printing it in an orientation that has no supports, but your layer line is in the wrong orientation. But supports also take time to clear away and can sometimes leave your part looking not so pretty. So you should consider what supports are going to be needed, and if you don't know, you could always just throw your part into a slicer and it'll show you exactly where the supports are going to be. But the short answer is anywhere there's overhangs. Whether that is overhang within the same part, right? If I have a hole sideways, there's an overhang being built here. Or if I have something that looks like a mushroom and I'm printing it upright, it will have overhang on the mushroom head. You can print overhangs of less than 45 degrees because as it makes the step overs, typically it will be able to build on itself. So you get a nice 45-degree angle or steeper. If you go more, you're going to start having some problems. And what do those problems look like when you print without supports? They look like spaghetti. You get a whole bunch of droopy lines on the undersides of your print. So when you're designing for 3D printing and you're looking at your part, you should keep these things in mind. What about for laser cutting? What kind of considerations do you have for laser cutting? There's one really big one. It was neither of those. The answer I got was not enough material and the laser. The thing to avoid is sharp corners, because when you are laser cutting, it is putting heat into your part, whether that's wood or plastic or metal, especially in metal, especially when you do industrial laser cutting. And those sharp corners, as the laser travels along the sharp corner and it tries to make a peak, right in that peak, it'll have a lot of heat for a much longer time than the rest of the part. And so you can get a lot of warping that happens right there on your part if you're not careful. Doesn't mean you can't do it. It just means you try and avoid it where you can. So if I was designing a gusset, see if I can draw sideways. If I was designing a gusset, which is just a little triangular piece that supports a plate that are 90 degrees to each other, right? So I have two plates, one that's upright, one that's horizontal, and I'm putting this piece of metal in the middle here. This gusset has the sharp corner right there and right here. So if I was to get this laser cut, am I in your way? Can you see? No. Okay. We will see what we can do about that. If I was to try and get this laser cut, then it's going to have a lot of heat right here and right here. So a better design that does not change the function is to just cut off the tips and give some straight edges here and there. And now I have no corners that are sharper than 90 degrees. And that doesn't change the function at all. So this is something you can do. Or you can fillet that corner. If it's a pocket, for example, maybe you just fillet that corner, and so it's not a sharp corner anymore. You put a little fillet there.
So basically just round that.
In general, yes. You want to round edges if they are sharper than 90 degrees. And that helps in a couple ways, because if you are handling these parts and you have sharp edges, your fingers are going to find out. So it's better for you to round edges where you can, especially because it takes no longer for the part to actually cut. When you have very critical holes, maybe you're pressing a bearing in, press fitting a bearing in, or maybe you need to tap the hole afterwards. You should probably undersize them for the laser, because laser cutting tolerances, especially if you get it purchased online, generally are larger than what you would want. So you undersize it, you make the hole purposefully smaller, and then you can just take a drill and drill right through it and make it the size you want. The hole's already mostly machined. By undersize, I mean something like 15 or 20 thousandths, which is how many millimeters? Anyone do the quick math? Half a millimeter.
2.
Half. Half a millimeter is roughly 20 thousandths. 0.5, that is correct. So make it half a millimeter smaller. You should also consider the machine's max material size. So this kind of goes with what Riley was saying. You have a cut area. I can't make a plate that is 3 feet by 2 feet if I can only cut a plate that's 2 feet by 2 feet. So when you are designing your parts, not generally a problem for FTC unless you have really small machines, but when you're designing your part, you do have to consider how big of a part can I actually machine. And then the last thing to consider is that laser cutting can only do 2D profiles. You can see here that it's doing an engraving, and sometimes you can get that to be the right depth, but I would not rely on that for making 3-dimensional parts in any capacity unless you have a really fancy laser. Most times it's only for cosmetics that they do that. When you're designing for a CNC mill, what types of considerations should you have there?
The radius of the bit for corners.
That is absolutely right. The biggest thing to consider is the radius of the bit for the corner. If I had, erase our gusset here. I have a plate of material or a block of material that I will move out the way in a second so you can see it. Oh, I have a block of material and I want to put a pocket in the middle of it. I want to put a pocket in the middle of the block. I've drawn in sharp corners, and I give that to a machine shop to make. And that machine shop is immediately going to turn around and say, I can't make sharp corners there. Why would they say, I can't make sharp corners there?
Because the drill bit is round.
In milling, it is generally called an end mill, but you are correct. It is a round piece of material that is going in from the machine head at the end of the spindle, and it's cutting this away. And so if I'm looking at a 2D profile, top down, that is a not very straight line. There. I have a tool that is going to be round. Maybe it's a half-inch mill or whatever, but it's going to go in, and it's going to cut along this edge, and it's going to go straight here, and it's going to go straight there. And as it does that, it generates an offset from the diameter of the bit, and I'm going to be left with a curve here. And I can go to a smaller and smaller bit all the way down to 1/1000th of an inch, but I will always have a radius there. With CNC milling, you cannot get rid of that radius. You can only make it really tiny. So the best thing to do to avoid what kind of concentrations? Stress concentrations is to make it as big as you can. Try and make it a nominal size or so. That way it's already accounted for. Now you can make these external edges sharp. Why is that?
Because the bit is going on the outside of the part and it's not
That is
coming in
correct.
from the
When this
inside.
bit moves here and it goes up, I can go past the part. I don't have to stop. And then I can come from over here and go that way. And I can move past that and I can leave sharp external corners. But I can't do any sharp internal corners. The other thing to consider whenever you're designing for milling is how are you going to hold it in the machine, right? If I have a whole bunch of funky curves on my part, I have to be able to somehow clamp that in a vise. And unless you have access to a machine shop that has lots of fancy clamps, it's going to be kind of hard to do that and hold it accurately, especially if you have to make modifications to it. So you want to leave yourself some flats somewhere so you can machine it, but also consider that in most mills that you have, they're going to be 3 axes, which is X, Y, and Z, and you will only be able to cut top-down views at a time. I could then take this part and I can rotate it to be where this side is up, and I can put another hole or a pocket in here on the side going that way, but I can only do 3 axes at a time, and the more features on the odd sides that I add, the more times I have to reset up this part. So a couple weeks ago, there was that picture of a whole bunch of different parts and bolting them together, and one way had them bolted all from the top and one had it bolted from all sides. It's the same kind of concept with machining. You want to try and make it all from one profile if you can. So if you can have it all top down and make all of your geometry there, that's probably what is best for you. Another thing to consider is that end mills and drills have a depth they can go. I can't drill into a 20-inch deep block of material without a special bit. I also can't cut a pocket into the 20-inch deep piece of material without special bits, because eventually my spindle is going to start getting in my way, and you can only go so long. It's not really something that you're going to come across in FTC because your parts are so small, but it is good information to keep in the back of your head. And then finally, as you can see in some of these pictures here, you can cut complex surfaces. I can make a nice smooth curve that looks like a wave in here. And you can cut that on a CNC mill with a ball end mill. But it's called surfacing, and it takes a lot more time to do it, and it's a lot more expensive. So you want to avoid it where you can. Looking at slicers, there's a lot of settings, and almost all slicers will have the same types of settings. So I pulled these from Cura, which is an open, a free software. I almost said open source. It's not really open source, I don't think. But it is a free software, and most printers have the ability to read any kind of G-code file, typically a text file, that you give to it. So you input your part, then you have a whole bunch of settings that you can change here, and the software does the rest. So looking through these settings, the first one that you're going to come across is layer height. What is layer height? Someone that's not Clara. That's exactly right. It's the height of one layer. As we talked about before with 3D printing, you're going to make a layer, and then you're going to move up a little bit, and you're going to make a layer. You're going to move up a little bit, and you're going to make a layer. What happens when you decrease the layer height?
It becomes smaller.
It does become smaller. The layers become smaller, but more specifically, it gives you more detail because you are taking finer passes. If you have a square part, you don't need more detail. But if you have something that looks really pretty and fancy, maybe you do need the extra detail. It also adds a lot more time because you have now increased the number of passes that the heater head, the extruder, these are all correct words, nozzle, hot end, extruder. I was thinking extruder. You've increased the amount of movements that the extruder has to do, and that takes more time. The next setting that you'll come across has to do with what they call your shell, which is your wall thickness. Your wall thickness is how thick your wall is. How many solid layers are you doing of your wall? As opposed to when you throw it in there, one of the settings we'll get to later is the infill. It takes solid parts and it hollows them out so that they aren't completely solid, and it fills it in with some pattern, which you can often change what that pattern is. And it's going to leave you with a shell, a solid section on the outside, top, bottom, and walls. So you can adjust how thick your walls are, which there's usually only one setting you adjust. You can either change the number of the thickness, or you can change how many wall line counts there are. Why does it say 2? Why does 2 wall line count give us 0.8 millimeter wall thickness?
So that the walls aren't just one layer thick. They're one layer thick, which is very fragile, and is actually the wall thickness used for tree saw supports, which are fragile.
That is correct, but how does 2 in this context correlate to 0.8 millimeters?
2.
Because each wall thickness would be 0.4 millimeters?
That is correct, but how do you know that it's 0.4 millimeters? I mean, that's correct. You can do the math and you can figure out that it thinks your walls are going to be 0.4 millimeters thick. But why does it think that they are going to be 0.4 millimeters thick? The answer I'm looking for is, and maybe I'm asking the question poorly, the nozzle size.
Oh.
The nozzle size is, in this case, set to 0.4 millimeters. That is a physical nozzle you have to change on your printer, and it will give you wider layers or thinner walls at whatever layer height you set it to, if your printer is dialed in correctly. And in this case, it has a 0.4 millimeter nozzle, which is pretty standard on most 3D printers. So if I increased it to 3 walls, what would that number go up to? Quick math.
What was it again?
If I increased it from 2 walls to 3 walls, what would my millimeter of thickness go up to? 1.2. That is correct. That is correct. And then your other settings are your top and bottom thickness, which are set to be the same. Generally, you want to keep your wall shell the same. There's no reason not to, unless one side's seeing a lot more force than the others. But it says your top layers and your bottom layers to get 0.8 millimeters is 8 layers. And why is that, as opposed to 0.4 or 2 layers to get 0.8?
Because that doesn't depend on the width of the layer. It's the height of the layer, which is set to 0.1 right now.
That is correct. If I change the top setting of 0.1 layers, it will change how many layers it takes, or how the number of layers it takes to get that same thickness. You're absolutely right. And then you have the setting horizontal expansion. You really don't need to worry about that too much unless you're really fine-tuning your prints. Infill. Infill is listed as a percentage. What would happen if I made it 100%?
It would be, the part would be full of PLA, and like our first print, it would take really long. It would be a really rough print.
It would take a long time. It would be a lot heavier than most of your other prints. That is correct. It would absolutely also be the strongest part that your printer could make. 100% infill is, I'm not going to put any hollowing out here. I'm going to make every single part of that absolutely filled with plastic. So it is the heaviest and the strongest your printer can make, and it probably is the longest that it will also take to print. I say probably because there are other things you can do to make it print longer, but relatively speaking, that is true. 15 to 25% is where most people put their infills, and they'll go up to 35 or 40% if you need a part to be really strong, but you kind of have diminishing returns after that because you're probably going to have a point of failure that is something not the infill, such as the layer lines.
It's not necessary to have that thick.
That is correct. You're putting a lot of time and material into something that you're not going to really get returns on. Infill pattern. This is a drop-down list, and every software will have different options. In this case, we have grid selected, which means that as it makes the different layers of, say we're printing a cylinder, a very oblong cylinder apparently, it's going to do the first couple layers of the wall and the bottom layers, but as it starts building up, it's going to get this cross-hatching grid pattern, and it'll look like a waffle in the middle. But there's other settings that you can do. Grid is probably good for most parts, and it's quick. That's why it's the default setting, is because it's quick. But if I hit this part with something kind of sharp right here, it only has the 2 layers on the wall there. Whereas if I did something that was, they may have one that's a cube, and it is like grid, but instead of this going straight up this way, it literally forms in the cube walls. And so you have a lot more points of contact as you go. So it's a lot stronger in general, because if I hit a point, it is more likely to be close to some other point already. So you can, if you're finding weakness in your part because of a very particular spot, you can either move your part on the print area so that it puts a grid where you want it to be, or you can change and play with your infill pattern, and there are lots of different infill patterns. They got some really funky ones too that are like swirls and whatnot. It's really interesting. Then you have material settings. What does when would you change your material setting?
When you're printing with like a different material? Or
That is correct.
like
Now,
something
what do you change your settings to?
whatever the spool says.
That's a pretty good answer. The spool generally tells you what you need to put your settings at. That's the manufacturer's recommendation for you should print at this temperature and have a heated bed at this temperature. Why do you want a heated bed? It does help with print adhesion. Do you have a different answer?
I was going to say print adhesion, but a more complicated answer.
For this class, we'll leave it at surface level. The basics are lots of people have problems with the first layer coming off and warping, edges coming up. And if your part breaks off the build plate, it will continue to try and print typically, unless you have a really fancy printer, and you'll have a whole bunch of spaghetti and not a part at the end. And you'll be very upset with your printer. So, not edible spaghetti. I would not recommend ingesting the spaghetti that your printer makes.
We're putting this on the internet, people.
Wait, they're printing out spaghetti dough, but the spaghetti gets cooked because the extruder's.
So, build plates. As you see here, it's a pretty standard setting, and most printers nowadays will either come with a heated bed or will come with some type of way of adhering to the bed to help counteract this problem because it is so prevalent. But your settings here should generally be set based on the manufacturer, and if you're having printing problems, the internet has lots of resources to help you fix those. Google does help. The next set of options is printer speed. When would you change your printer speed?
When you're printing something complicated and you want to make sure it prints properly, then you would make it slower.
That is a very good answer, and that is absolutely correct. If you're printing something that you need it to take its time and you don't want to have to print it over again, you might slow down your speed. You could also make it faster if the opposite is true and you don't really care. Say that again? In some cases, yes. If you're prototyping something is a good answer. If you don't really care what the surface looks like, you might be able to bump it up so that it happens faster. Most times you're going to leave it alone. You're going to let the software use its preset speed because that's what it's been dialed in for. You have Z-hop when retracted as your next option. What does that do if I check that box?
It moves the entire gantry, like moves the head of the printer up when it pulls the filament out of the nozzle. That way it won't accidentally brush up against any of the already printed
That
stuff.
is correct. So you have, maybe we passed it up. Oh, I did pass it up. There's an enable retraction as part of your material. And what that does is you may have some back pressure of melted plastic that's just going to droop out. And so as you move, generally you will enable retraction, so it backs it up a little bit, and you end up not having these little strings all over your print. So what Z-hop does is when it does that, it also picks up the head. And I've always found it useful to enable it. It does add some time, but the time's usually worth it because sometimes it might hit a wall, which you don't want it to do because the plastic is dripping out of it, and it's usually very helpful to turn it on. Cooling. There is a checkbox to enable print cooling. Do we want to cool our print?
Yes.
Why do we want to cool our print?
So when you take it off the bed, it won't flex when you take it off the bed, because if it's still warm when you take it off the bed, then it will warp.
That is true. You do want to let it cool completely before you take it off the bed. But in this case, the setting is related to cooling while printing, which is generally a little fan that's pointed right at the hot end. And generally, yes, you do want to turn it on because, especially if you're doing small features, it will cool the plastic, move up, and try and put more plastic on before it's cooled if you don't have that fan on. And that can induce warping by having stressed because as plastic heats and melts, it expands, and as it cools, it contracts, and that contraction makes it want to pull on itself. So generally, you want it to cool quickly so that you can avoid that. When would you want to turn that off?
When you're printing bigger prints?
No, not generally. It does help it's not going to add any time to turn that fan on. And so having a bigger print, it only ever helps. You generally want to turn it off if you have some kind of specialty material that needs to be at a certain temperature to prevent it from warping or whatnot. If you have an entire chamber, that's a very specialty setting that you'll probably never touch. And then you have supports, which in this case they break it down into support and build plate adhesion. Supports have a checkbox that allow it to generate supports. You can try and print a part with no supports, and if it needs supports and you don't add it, what happens? Spaghetti, that's correct. You get spaghetti. Your printer turns Italian.
It's a me.
You have options within Cura, and probably other slicers as well, to look at the overhangs to see if there are areas that need supports. Or you can just turn on generate supports, and in this drop down, I have it set right now to everywhere, but there is one for overhangs only, and it will only put supports on the overhangs, and if it doesn't need supports, then it won't add them. So these softwares have gotten really good at adding supports. Generally, when it prints a support, it will move up and skip one layer. Why does it skip one layer whenever between the support and the actual part?
To make sure that the support comes off cleanly from the part.
That is correct. Some very smart people have figured out that if you move up one layer, gravity will set it down on top of your part just fine, and it'll look just fine, but it makes it a lot easier to remove, so it's not so adhered to your part. We used to have to take knives and literally scrape them off. They didn't break away, but that's just me being old, I guess. And then you have a support overhang angle. So this is a setting you can change where if you know your printer can do 50-degree support angles without support just fine, then you can set it to 50. If you know it can do 60, you can increase that. So that's how it determines when supports are needed. And build plate adhesion. There are two build plate adhesion types that are the most common, and that is what? Who knows what the settings are called?
Brim, skirt, and raft.
Oh, that are three. Wow, you hit all three of them. That's fantastic. Okay. Do you know what each of them do?
I think a brim is just a line around it, right?
Okay.
Oh, skirt is the line around it. Raft, I'm pretty sure is like a whole plate underneath it. I don't know what brim is.
Clara seems to know what brim is. What is brim?
Brim is where there's a layer of material all around the base of the part. Raft is when there's a layer of material under the part, and skirt is when there's one single outer layer of material around
And
the
when
part.
would you want to use each of them?
It depends on, like, the skirt is so that the extruder can get a piece of plastic out before it prints the actual part, so it already has material fed through it. Brim is usually if you have pieces like on the very edge that could potentially peel up from the build plate, and at least that's what I've used them for.
That's correct.
And raft is when you want the bottom of your part to not be touching the build plate, and so you use the raft for that instead.
So most of that is correct. I would say 95% of that is correct. Skirt, as your nozzle heats up, which is generally the first thing your printer does after it homes, it moves to a position, it starts heating up the nozzle. And it's sitting there, and at some point the plastic actually starts melting a little bit, and so it'll start dripping a hair. And most people will remove that, but that means that there's an empty spot in your nozzle that is not filled with plastic. So the skirt helps it start pushing material through so that as you start printing your part, you don't have this little gap of a layer line missing. Brim is, you are correct, when you have some issues with build plate adhesion, it will start out wide and it'll give it a much wider base so that it has more surface contact in order to adhere to it. When I've used raft in the past, it's because I could not stop the warping no matter what I did. Even brim would not. Skirt would not do that. And it basically puts that warping. Maybe I have a particular spot on my bed that needs to be fixed, but it's just a low spot, and so it always pulls up from there. It puts that warping in the raft so it's not on your part. So that's when I've used raft before. Your answer is probably also correct, that if you don't want it to have some of the surfaces, or maybe the print beds are glass, or they have a texture to them and you don't want that on your part, maybe you want to put a raft instead so it's more uniform for cosmetic reasons. But I've used them for when I just can't get it in that one particular spot to get here, and I know it's going to warp, and so I put that warp onto something that I don't care about, sacrificial material. That's a quick run through of 3D printer settings. Are there any questions related to slicers? Excuse me. Excellent. Moving on to game strategy. The most important rule in game strategy is what? That is an excellent answer. Why is the most important rule to read the game manual? But why is it important to know the rules? Give us an answer. Riley has an answer. Why is it important to know the rules?
So that you don't do something that you didn't know.
That is a good answer. It's not the answer I'm looking for. I'll give you a hint. The answer I'm looking for pertains to what we talked about 2 classes ago.
If you don't know the rules, you can't play the game.
That is also a good answer, but not entirely true, because there are people who show up to competitions that don't know the rules that do play the game. The answer I'm looking for is defining your problem. If you don't fully define the problem, then you can't fully solve the problem. So the first step in your engineering process is to define the problem. And you do that by reading the game manual, because they've already defined the problem for you pretty well. You just have to know all of the ins and outs about it. Realistically, there are some game strategy items that you should consider. The first one is that you need to be able to effectively communicate with your alliance before the game. So you need to be able to go to your alliance partner and have a way of talking with them about what your strategy is going to be. Why do you even need a strategy?
So you can play the game well and win?
That is correct. In FTC, what gets you ranked highest to be able to pick an alliance member is winning the game, more than anything else. Points matter second to winning, which is counterintuitive, but points also get you a winning score. So they are important, but they're not as important for winning in order to rank highly. If you go into a game and you try and play the game without having a strategy in mind beforehand and just hoping for the best, how do you know what it's going to take to win? You won't. You're just kind of hoping for the best. But if you lay out a strategy and say, this is what we're going to do, especially if you talk with your alliance partner about it ahead of time, then when you actually go into the game and you follow through on that, you'll find that things generally go a lot smoother that way. So you should make a system for planning with your alliance. Last year, for Microchips and Queso, we had a sheet that we called the menu, and it had 6 different auto paths laid out in picture for what our autos were pre-planned to do. And that made communicating with other alliances really easy, because they could tell us which one they wanted us to run so that we didn't run into them during autonomous. And we just showed them the sheet and said, what do you want to do? Which one of these do you want us to run? Because we know all of them work. The next thing you need to be able to do is effectively communicate in-game, especially with the human player. It's really easy to practice in your garage or at your school with not a whole lot of noise around, but when you're in an actual game setting, there are lots of people yelling and cheering, and the human player may not be able to hear you. So you need to practice speaking loudly, or practice a way of communicating without having to speak to them. I know that our mentor team had little blocks for the pixel colors last year, and they would put the different colors that they wanted from the human player facing towards the human player so that they didn't just have to yell it, but they also had a visual indication of what was required there. You should have a goal or a plan before the match starts. It's not great to come up with that when you're standing there waiting for the autonomous to run. You should definitely plan that ahead of time. You should coordinate your autos with your alliance partner if you can, especially at competitions. There is always a practice field. You book time on the practice field between your matches, and you get your alliance partner out there. And if you aren't certain if your autos are going to be able to work well together, you run them at the same time, and you find out. Because if you don't find out on the practice field, you will find out in the match whether they work or not. And that's not generally the place you want to find out whether they work or not. Sometimes it's better to have one person run an auto that is going to work than have two people run autos that might work and end up having them crash together and getting no points for the alliance. A very good game strategy when you are starting out and you are designing your bot from the beginning of the season is to aim for the most amount of points with the least amount of challenge. Why is that a good game strategy?
Because you win with that strategy.
Because points win matches, and winning matches gets you ranked highly, so you can pick an alliance partner who scores really well. And that's how you move on through all the different seasons, through all the different levels. If you are looking to do it based on your gameplay, more so than awards. FTC really focuses a lot on the awards. An equal or slightly greater part of the rankings, or the advancement rather, is based on the awards and your submissions. So you should be spending a lot of time on those as well. But if you are looking to do it based off gameplay, you need to score at least higher than everyone else. And if you figure out how to do high scoring early on in the season, at least compared to where everyone else is, you will put yourself in a better position from the beginning. And then the last one on there is to read the game manual. My mentor, when I did FRC, told me that rule number 1 is safety first. Rule number 2 is read the game manual. Rule 3 is read the game manual. And rule 4 is to read the game manual. So that has stuck with me since I did FRC way back when. It is important to note that your alliance partner for one match can and will be your opponent in the next match. So while you are working with them, it is critical to note how well they play, both with you and against you, because one of the things we learned as a rookie team is that alliance selection is very challenging and happens very quickly. So you may not have time to have a full scouting team. You may not have the people to have a full scouting team, but you don't fully need a full scouting team. But it is better to know you work well with someone and have that synergy than to just pick someone that is ranked highly in general. That's all I have for you today. This is a little bit of a shorter session, but are there any questions from the audience related to DFM, related to 3D printing, related to game strategy, or FIRST in general?
Should we read the game manual?
I think it's so important that maybe you should go back and read the center stage game manual now that the game is over, just to make sure you fully understood what you were trying to do. I think it's important.
And Q&A.
And Q&A, that's correct.
What's the most important part of the game manual?
That's a good question. What's the most important part of the game manual?
The table of contents?
I was gonna say, the teller that has all the pictures of which scores count, which don't.
Do you have an answer to that, or is it just an open question?
I wanted to hear their answers, but it's also, what do you need to do to pass robot inspection?
If you don't pass inspection, you don't compete. It doesn't matter how well your robot scores at home or even in scrimmage matches or whatnot. If it can't officially compete, it doesn't matter. You will not advance. It's real sad, but it's true. So make sure that you are within inspection and try to avoid being right on the edge of being within inspection. If you can give yourself an inch or two in every direction and make sure that you have that extra room, you don't have to chop up parts of your robot at competition in order to qualify. And everyone in the room is laughing because everyone has been there, including myself. We have had to put, in FRC we had a weight limit, and we showed up and we were 2 pounds overweight. And we had to take one of our plywood sheets and make it Swiss cheese. And it's not a fun position to be in. So don't put yourself in it. Any other questions? You are now deemed mechanical engineers in training. FTC qualified. You have the essentials. Now we're going to move on to the advanced class. No, I'm just kidding. Excellent.